Hi everyone, my name is Hila Manor, and I will present today our work Zero-Shot Unsupervised and Text-Based Audio Editing using DDPM Inversion. This is a joint work with my supervisor, Tomer Michaeli. As diffusion models gain traction for generative tasks, a lot of recent attention has been given to editing real signals with diffusion models. In the image domain, there are two main approaches for such editing. The first is the training and fine-tuning approach, where you train a model from scratch for editing or fine-tuning a model on new input samples. The second allows editing without fine-tuning or training in a zero-shot manner. These works are much more efficient, and the editing quality can be just as good. However, in the audio domain, all of the works seen so far lie in the training fine-tuning regime, which is expensive in compute, time, and training data, and zero-shot approaches were not proposed. In this paper, we propose two editing approaches. The first, which is very common in the image domain, is text-based editing. Here, we textually describe what should change in the excerpt, for example, the genre of a song. Text-based editing is limited to things that can be even described in text, and can, for example, modify the melody of a given track. For these kind of edits, we propose an unsupervised editing approach, which discovers interesting and varied editing directions, given an input signal in a completely unsupervised manner. The two approaches complement each other and enable modifying elements that are both easy to convey in words and elements that are not. Let's hear what these two approaches will sound like on Beethoven's Ode to Joy. To understand the methods, we need to briefly go over diffusion models. In diffusion models, we have the forward process, where noise is added to the signal step by step, and the reverse process, that learns to denoise the signal step by step until a new signal is created. In text-to-audio models, you can also supply the denoiser with a prompt that helps guide the generation. Since the model is deterministic, what determines the output signal is the text prompt, the initial noise maps, and the noise maps along the way. Therefore, if we want to affect the output signal, we need to change either the text or the noise maps that created it. The two approaches we propose leverage both of these options. The problem is that the reverse process described so far describes generation of a synthetic signal, whereas we are interested with editing real audio signals. For this purpose, an inversion process exists, which takes an audio signal and tries to predict from it what are the noise maps that would have created it. Now it's easy to understand how to apply text-based editing. First, apply inversion with or without a text prompt describing the original signal, and when you regenerate the signal, just keep the noise maps the same and change the used text prompt. We can also start from some time step along the way, which will affect the strength of the edit. This approach is an extension to the audio domain of the approach that appeared in the original DDPM Inversion paper for images. Our work reveals that this approach is quite versatile to domain transfer. This method allows changing global elements, such as the genre of a rock song, to a jazz song. Or, for example, change the instrumentation from trumpets to banjos. We evaluate our data editing with quantitative measurements and show our method outperforms state-of-the-art editing approaches, both in terms of text adherence and in terms of similarity to the source signal. We also conduct a user study and show users preferred our edits over all compared approaches. We will now present the unsupervised approach. Here, we would like to somehow affect the noise map branch of the reverse process. For this, we turn to the results from our previous work. There, we tackled the problem of non-blind Gaussian denoising. We showed how we can take a pre-trained denoiser trained to only denoise an image and extract without any training the posterior principal components by just using forward passes. These principal components unveil the modifications with the most uncertainty, for example, here the openness of the mouth. Since each time step in a diffusion model is a non-blind Gaussian denoiser, we adapt this result to diffusion models. So, after DDPM inversion, we first extract the principal components at each time step of the reverse process. Then, as before, we can regenerate from some starting time step while adding the extracted principal components along the way, keeping the noise maps the same. We can add principal components all the way to the end or up to some ending time step and stop adding principal components from it. The use of different time steps affects the globality of the edit. Edits applied in this approach show a wide variety of semantically interesting effects, such as taking this original signal and removing the singer. Or, for example, something that is most prominent in music, taking this original signal and changing its melody. Different principal components extracted for the same signal carry different semantic meanings. Here, for example, the first principal component moves the emphasis from the singer to the guitar, while the second principal component moves the emphasis from the singer to the drums. As the first proposed zero-shot unsupervised editing approach, we propose to use ST-edit as a baseline. Zeus editing achieves higher quality for every desired editing strength. We additionally show that the Zeus approach is also applicable for the image domain, extracting semantically interesting editing directions. Here, for example, we show directions that transform the machine gun to a peaceful bonsai tree or the cat to a dog. You can check out our project webpage and paper for more results and in-depth discussions. Thanks for listening, and I'll be waiting for you at the postal session.